Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. In this video, I am going to talk about solvent extraction. So what is solvent extraction? Solvent extraction is also known as liquid-liquid extraction. Liquid-liquid extraction is a method to separate compounds based on their relative solubilities into different immiscible liquids, usually water and an organic solvent. So, importance of the process. Solvent extraction, in short form AC, process was first developed as a tool of analytical chemistry. Every metallic element of the periodic table could be virtually separated by these methods. Back in 1940s, solvent extraction was primarily used to separate nuclear and rare earth elements. However, the availability of inexpensive and effective reagent led to the establishment of large-scale solvent extraction process for extraction of non-ferrous metals from hydrometallurgical leach liquor. Now, solvent extraction consists of transferring one or more solutes contained in a feed solution to another immiscible liquids solvent. The solvent that is enriched in solute is called extract, and the feed solution that is depleted of solute is called raffinates. So feed solution plus solute, raffinates, solvent, extract plus solute. Now, solvent extraction is a part of hydrometallurgy. Leach, extract, steep, reduce. Ore, waste, mixed metal solution, raffinase, selected metals in organic, cyclic extraction, selected metal in aqueous, recycled steep solution, spent electrolyte, and reducing agent metal values. So you can see the loaded extractant equals raffinates, setting chamber, water immiscible extract solutions, metals bearing equals solutions, mixing chamber. Now, types of solvent extractions: solvating extraction, cationic exchange, anionic exchange, and chelating extraction. You already know about the cationic exchange and anionic exchange because water purification working on this cationic and anionic exchange. So first we will discuss about the solvating extraction. Solvent use: tributyl phosphate TBP, trioctyl phosphine oxide TOPO, methyl isobutyl ketones. The applications of this solvating extraction: separation of lead, zinc, and uranium, iron, cadmium, hafnium, zirconium, and plutonium. Cationic exchange: solvent use: di-2-methyl phosphoric acid, naphthenic acid, and versatic acid. Application: extraction, separation of copper, zinc, nickel, cobalt, silver. Anionic exchange: solvent use primarily amine, secondary amines, tertiary amines, and application: extraction, separation of uranium, thorium, vanadium, and cobalt. Chelating extraction: solvent use LX63, LX65, KLX100. You can see the structure of KLX100, which contains one quinoline rings, one hydroxy groups, and alkyl groups. Application: extraction, separation of copper, nickel, and cobalt. Two basic steps of extractions, solvent extraction. Extractions, you can see these equations, and stripping. So solvent extraction of uranium, you can see impure acidic uranyl nitrate SPG 1.3. It is going in, and raffinates thorium, molybdenum, daughter's tungstens coming out. And this meanwhile, saturated tributyl phosphate, you can see it is inlets, and clean water, you can see pure uranyl nitrate solution and clean tributyl phosphate SPG 0.85, and you have the pump here. So distribution coefficients, how you will calculate KD values. At a certain temperature, the ratio of concentration of a solute in which of solvent is always constant. This ratio is known as distribution coefficient Kd. So Kd is equal to concentration of metal ion in organic phase divided by concentration of metal ion in aqueous phase. Organic phase and aqueous phase, S organic is aqueous Kd. Organic phase, aqueous phase, you can see HL, organic, MLN, ORG, then Kd value HL, and a lot of things happen in aqueous phase and organic phase. Extraction equilibrium. For chelating reagent HR, the extraction reaction for metals ion Mn plus can be represented as M equals N plus NHR organic. It is in equilibrium with MRN organic plus H plus equals. So extraction constant Kx is given by Kx is equal to MRN concentration of organic layer and aqueous layer of hydrogen H plus ion concentration, then metal N plus equals and HR N organic. So extraction constant can be expressed as with this formula where Kd is equal to MRN organic divided by metal N plus equals. So extraction constant can be expressed as log Kd is equal to log Kex plus Nph plus N log HR organic. So extraction coefficients, it indicates how much of the metal will move from the aqueous phase to the organic phase in a single contact. Effective extraction coefficient can be expressed as EF, Mn concentration of organic, volume organic, Mn plus equals and volume equals. Now single stage versus multi-stage. Single stage AC. Single stage process is commonly followed in the laboratory scale. Contacting is carried out by the taking two phases together in separating funnel, followed by the vigorous agitation so that the phases may disperse in each other as a fine droplets. Ceasing the agitation lead to the separation of phase in two distinct layers. You can see here before extraction and after extractions, organic compound is solvent layer and aqueous layer, solvent layer and organic compound in aqueous layer. Now, single stage solvent extraction. From mass balance, it can be shown that X naught divided by X is equal to 1 plus Mn plus organic, Mn plus equals volume organic, volume equals, where X0 concentration of metal ions in the feed solution, that is the aqueous phase before any contact. Then X1 concentration of metal ion in aqueous raffinate and the aqueous phase after a single contact. Now from mass balance, it can be shown that X naught divided by X1 is equal to 1 plus EF, where you know the concentration of metal ion in feed solution, that is the aqueous phase before any contact, concentration of metal ion in aqueous raffinate, that is the aqueous phase after a single contact. Now multi-stage counter-current solvent extraction. The extraction of metals on industrial scale, multi-stage counter-current solvent extraction proceeding is followed. The aqueous raffinates from one extraction unit is fed to the next unit as the aqueous feed, while the organic solvent flows in the opposite direction, thereby picking up more metal ion in successive contact, dividing the organic phase into small parts and making multiple contact in the most efficient way of extractions. So, for single contact, X naught divided by X is equal to 1 plus EF. So, the multi-stage contact assuming N contact, X naught divided by Xn is equal to 1 plus EF divided by N power N. Now, as limit N tends to infinity, Xn divided by X0 is equal to 1 exponential EF is equal to exponential minus EF. So, multi-stage contenting is best. So, multi-stage counter current solvent extraction, you can see the organic phase, you can see the aqueous phase situations. Extractions, and then aqueous mediums. So McCabe diagram, equilibrium line, operating line, and theoretical stage. Weight ratio of the solute solvent in raffinate phase and weight ratio of solute solvent in extract phase. Now, selections of organic solvent: highly extractions capacity, selectivity, easily steeped, immiscible in aqueous phase, sufficient density difference with the aqueous phase, low viscosity, non-toxic, non-explosive, and cheap. Diluents. What is diluents? Diluent is required for dissolving or diluting the organic extract, and so that its physical properties like viscosity and density become more favorable for better mixing of the two phases and their separation. Aliphatic or aromatic hydrocarbons or combination of both are used as diluents. Diluents affect the extraction, scrubbing, stripping, and phase separation process quite significantly. Example of some common diluents: kerosene, benzene, chloroform, xylene, naphtha, toluene. Now, equipment for solvent extraction. Mixture settler. So you can see in this diagram, we have the rotations, we have motor with mixing impeller, mixing chamber, we have mixture impeller, light phase inlets, heavy phase inlets, seating chamber, we have this light phase filler, adjustment heavy phase here. Now, equipment for solvent extraction: column, contractor. Column extractor, light phase out loaded organic. Interface control, light phase in organic feed, heavy phase out raffinates. Now you can see the equipment of solvent extraction: centrifugal contractor. So at the end you can see the applications. What is the application? Today the process of solvent extraction is widely applied in the miscellaneous field of the science and technology. Analytical chemistry, extraction of rare earth and PGM, wastewater treatment, mineral oil treatment and dewaxing, food industries, essential oil extraction, perfume industries, fragrance extraction, and pharmaceutical industries. Now conclusions. In spite of having the advantage of rapid extraction kinetics with the feasibility of recycling the solvent, there are some drawbacks of this process. Use of toxic and flammable organic diluents. Sometimes cost of solvent system becomes too expensive. In several cases, there is a loss of organic solvent in the process. Solvent extractions may not pollute the air as much as other pyrometallurgical process, but a lot of toxic chemicals find their way into the water bodies, polluting them. The extensive application of solvent extraction has become a field industries of its own, with proper modeling of the process, invention of new equipment, use of more effective extract, and better understanding of the science behind it may lead to it to be one of the most important extraction process in the metallurgy. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.